Okay, so let us then start this class 2 discussion. Okay. So basically in this week 2 lectures, mostly you have covered the topics of mean free path, the collision of gas molecules. So you are dealing with still the kinetic theory of gases chapter, and mean free path is a very important idea of that, important concept of that particular chapter. So this week's assignment is mostly based on that idea, that mean free path, and then collision frequency, and then what is the that fraction of molecules surviving after a collision. So the problems are mostly related to those concepts only. So these are almost all numerical problems. So we have 10 problems as usual, and which we will solve together. And then in the end, I will give you maybe one or two extra problems if there is still enough time left for us to discuss. And then if you have some doubt, you can unmute yourself and ask me, and I'll help you. I'll try to help you to clarify them. Okay. So basically, also one thing I want to discuss, I want to like state before starting this class is that in the last class, probably that I don't remember who asked that question, or maybe that person is not present right now, but I'm still saying it in the starting of the recording. So if somebody watches it later on, he can also find out that in the last class somebody asked a question that is this kinetic theory, or sorry, the equipartition energy theorem, and this whole thing of this Maxwell velocity distribution, are those things um, applicable for diatomic gases, or more than two atoms, like more than one atom, any multiple atom gases, is molecules, is that possible or not, or is it only valid for monoatomic gases? So to which I replied that they will be valid for other cases as well. uh, but I think the most like uh, exact answer will be that of course they will be valid for even diatomic, triatomic, or more than that atomic gases also, but this will be most accurate for monoatomic gases. And the reason is that if you remember in the Maxwell's velocity distribution, there is something like let me just write it down before I start this week's lecture content. So Maxwell's velocity distribution, this idea, if you look at the derivation of it, you will find out that they deal with something as the linear momentum, change in linear momentum, from which they calculate the force basically. So the idea is that if there is a wall and there is a particle that is hitting that wall, is a gas molecule that of mass m and velocity is u, it is hitting the wall, and then it is again coming back as a at a same velocity but in a negative minus sign because of the opposite direction. So what happens is that what is the change in momentum in this case, which is like, if we are only talking about one dimensional cases, then it is, let's say, x direction. So the change in the momentum by this process in this x direction will be like mu minus of minus mu, right? So this is the initial momentum mu, mass times velocity, and then the final momentum is minus mu, because then the velocity has become negative because it is in the reverse direction, and their difference is the change in momentum. So this is just 2 mu. So 2 mu is the change in linear momentum in this collision process. Okay, and if you find out that in the Maxwell's velocity distribution there are considered all three dimensions x, y, and z, but the basic idea was based on this linear momentum thing, that what is the change in linear momentum if a certain process such like that is happening, and then the derivation went on further, but the derivation had this part as an important concept. So this kind of a thing is only valid when the motion of the molecule is, like just I said, is a uh, like linear sort of motion, like a translational motion, like if the molecule either is moving in the x direction, or it is moving in the y direction, or it is moving in the z direction. So this is only valid, or this derivation is valid. Derivation not valid, I'll say that derivation is done, the Maxwell velocity distribution is done based on the concept of translational motion of the molecules. Okay, translational motion of the molecules. That means either it is getting translated in the x direction or y direction or z direction. So this kind of a thing will come only in that case. But if you think carefully, there is nothing considered like rotational motion or vibrational motion as such. At least nothing like that is considered in the derivation of Maxwell velocity distribution formula. So, but rotational or vibrational motions are not taken into account, right? So if that is the case, then we know that for monoatomic gases, the only kind of motion that is counted in the degrees of freedom of that monoatomic gas is basically the translational motion, because for monoatomic gases case there is only a single atom in a molecule. So this is a single atom in a molecule that the molecule is consisted of. Then this molecule can have either motion, translation motion in x direction or y direction or in z direction. It can have no other motion because the degrees of freedom is defined like that. So degrees of freedom will be like 3n minus m, where n is the number of atoms. So in this case it is 1, and m is the constant, which is in this case is 0, because there is no other constant present for the molecule to move in any particular direction. So the degrees of freedom is 3, and the 3 comes for the 3 directions like x, y, z directions, these 3 directions of linear or translational motions, which will be these kind of a motion. But if, let's say, for the simplest case, if there is more than one atom, let's say the first case we consider is diatomic, then obviously there are two atoms that are like forming a single molecule. So it has two atoms, atom 1 and atom 2, and they have a molecular bond in between them. Like this is a constant that is present here because they are connected like that. So this is m equal to 1, number of constant 1, and number of atoms is 2. So here the degrees of freedom was sorry. So the degrees of freedom was 3 into 2 minus m. So this was like 6 minus 1 is equal to 5. And this 5 degrees of freedom is basically consisted, this basically like contains all 3 directions of translation like x, y and z direction. But there are still 2 extra degrees of freedom, and that comes from the rotational degree of freedom of that total molecule. So basically this total system of 2 atomic molecules, diatomic molecule, they can either translate in x direction. So this is a single system, let's say, which has 2 atoms. Either they translate in x direction or y direction or z direction. So these are forming 3 translational motional degrees of freedom. Translational motion degree of freedom. So 3 comes out of there, but there are still 2 left out of this 5. So these 2 are plus 2 extra rotational degree of freedom. Why we are saying rotational degree of freedom? Because this molecule, because this has formed a structure like this, so this can either rotate in, how this can rotate, so it has a axis that it has to maintain, that this is the axis that is the connecting link between the two atoms basically. So that is the constant. So they cannot rotate in that direction, but actually they can rotate along the other 2 axis directions. Like they can either rotate along x axis, either taking the y axis as a rotational axis like this, or as a z axis as a rotational axis like this. But they cannot rotate along this direction, because then the constraint between the 2 molecules, because this diatomic molecule, 2 atoms are linked by a bond, so they cannot avoid or they cannot exceed that. So because of that, along x it is not possible, but y and z are free to be the rotational axis. So these are the 2 extra rotational degrees of freedom which becomes evident, or which comes into the picture as an extra when you are considering more than one atom. Like for the simplest case it is diatomic. But this rotational degree of freedom, this rotational motion, nowhere in the Maxwell's derivation this rotational motion is being taken into account in the calculation. It's not taken into account in the calculation for Maxwell's velocity distribution law. So because of that, even if we can still apply this Maxwell velocity distribution to the atomic molecules as well, but because these additional degrees of freedom are not considered into that calculation, so the result will not be very accurate. I mean, the match between the the calculation result and the actual system's behavior will not be very much accurate or very much in sync. But in monoatomic case, because there is only three translation degrees of freedom and all three of them are taken into the calculation of Maxwell's velocity distribution law, so therefore for that case it will be the most accurate in terms of consistency with the calculated thing and the actual thing in like what is happening with the system itself. But for diatomic, triatomic, and more you increase the atom, there will be additional degrees of freedom which are not of course taken into account for the calculation. So that's why they can differ and vary from the actual calculated result, and the error will be greater. So the accuracy will decrease as soon as you increase from monoatomic to higher atomic molecules, right? But the validity will still be there. Only this was the thing I wanted to clarify before starting this session. Now so basically let us start with this week's thing that we have to discuss. So as I said that this will be mostly based on mean free path and collisions, etc. So let us read the first question. Now first question is that calculate the fraction of molecules which have the mean free path in the range lambda to 2 lambda. Okay, so this is a very simple one line question, but let us analyze the question first and try to understand what it tries to ask you in the question. So basically it's saying that what is the number of molecules that having mean free path in the range of lambda to 2 lambda. So basically you know one formula from the mean free path, I think. So this is n equal to n naught e to the power of minus x by lambda. This equation is famously known as survival equation of the gas molecules. Why it is called survival equation? Because if n naught is the initial number of molecules present in that gas, and after traveling x distance, the number of molecules that will be still present in that cluster without getting knocked off by collision or anything will be n, where lambda is the mean free path of the gas molecule. So basically if you have a system of gas molecules, so if you have a container, gas molecules are randomly distributed everywhere, right? So if you consider like say only one molecules, if you observe its trajectory, then you will see that it undergoes through some kind of a zigzag sort of a motion. So like this and then like this, so anything like that. But so basically, and free path, you know that free path is basically the path distance that the molecule traverses between two successive collisions, right? But since it has a zigzag kind of a motion, so the path distance that it traverses between this here to here is, let's say, x1. Then from here to here, it again traverses a distance which is different, which is, let's say, x2, and then x3 and x4. So many possible values are like that. And again, there is not a single molecule in the gas, but there are many molecules present in the gas. So what is done is that you integrate everything and you take an average value of that free path. So basically, let's say if x1 is the path distance covered between two successive collisions for, let's say, dn1 number of molecules, right? Similarly, x2 is the path distance traveled between two successive collisions for dn2 number of molecules. And similarly, if you keep on doing this, so we'll see that the average distance between two successive collisions equal to x1 into dn1 plus x2 into dn2 plus x3, some xn. So it can continue as much as number of molecules are present there. So let's say this is and then divided by the total number of molecules present, like that. So dn1 plus dn2 plus 1. But this is in a discrete case scenario, but in reality the velocities will not be discrete like that. In classical sense it will all be continuous, because in classical sense energy is also continuous. So by that fact you will see it like a continuous distribution instead of a discrete thing. So what we'll do is that instead of summation you take an integral where you integrate over x times dn integration, and below you average it out by integration of dn. So you know that this is the n naught value, because this is the total number of molecules present in the system initially without any collisions knocking off any molecules. So total number of molecules present at first, then xdn. So this is how you do, and how you calculate your mean free path is lambda. Sorry. So this is your mean free path lambda. But actually if you say that this is the mean value of all the possible free paths possible over the total all the possible molecules present in that gas, right? But what is the, then this, if this is a survival equation, then it claims that if mean free path is already taken as lambda, and initially before any collision started, initially at let's say initial time, let's say t equal to 0 and x equal to 0 also it has not started traveling any distance, if total number of molecules present is equal to n naught, so then after traveling x distance, how many number of molecules will still be remaining in this group, like the group of molecules started with, that number is n naught. So how many will survive is basically, this is the same number of molecules, this is basically the answer is the number of molecules that survive or do not undergo any collision within distance equal to x. So then we can say that the fraction of molecules is n by n naught is the fraction of sorry okay, so let us continue from where we left. So I was discussing the first question, which was like this question that calculate the fraction of gas molecules which have the mean free path in the range of lambda to 2 lambda. So I was saying that you have to use the survival equation for this, which is this main equation regarding mean free path. This is this equation, n equal to n naught e to the power of minus x by lambda. Now this n by n naught is the fraction of molecules that has survived from any kind of collision up to this distance x. Lambda is the mean free path, x is the distance that the molecules has traversed, and after that distance the number of molecules that has still survived the collisions are n, and n naught is the initial number of molecules. So if you have to calculate the fraction that has survived, that is from the survival equation is n by n naught, which is equal to e to the power of minus x by lambda. Now roughly you can say that this many number of this fraction of molecules, this fraction of the number of molecules has the free path length of at least x, because up to x distance, as if they have not undergone any collision, then after that if there are collisions, then that will knock some molecules off in n, but till x distance this n number of molecules has not gone through any collisions, or they are not knocked off from that total group of particles, right? So if that is the case, then the question was the lambda to 2 lambda range. So basically you have to take x equal to lambda once and x equal to 2 lambda once, and then see what is the fraction for both the cases, and then in between the range, if you have to see if you have to calculate, then you have to just take the differentiation of differentiation means the difference of both of the fractions, because you have to then you will get the exact fraction that is in between that range. So first of all, fraction of molecules within lambda distance, that is x equal to lambda here, is equal to e to the power of minus lambda by lambda is equal to e to the power of minus 1. Then the fraction of molecules within 2 lambda distance, that is here x equal to 2 lambda is equal to e to the power of minus 2 lambda by lambda is equal to e to the power of minus 2. Hence, the fraction of molecules having free path within lambda to 2 lambda is just the difference of these two. Now remember here, this lambda, the mean free path value does not change, right? So that is fixed because that is the average value, which is this denominator in e to the power of minus x by lambda. This does not change. Only variable is x. X is the distance that is being traveled. So that is being varied as lambda and 2 lambda in the question. So the answer will be the difference of these two quantities, which is e to the power of minus 1 minus e to the power of minus 2, which is like 1 by e minus 1 by e squared. Now just take the difference and you will calculate. You will see that this difference will come around 0.23, which is your answer. So let us choose the option then. So your right option will be here. This is mentioned that 0.23, this is the correct answer. D, we have got also that. So this is 0.23. So this is done. Now let us move on to the second question. It says that at STP, which is the standard temperature and pressure, just like NTP and STP are almost the same, you have to take a standard value of temperature and pressure, that is standard in this case. So even if there is nothing specific value mentioned, but you have to know what is the STP pressure and temperature value. And at that pressure and temperature, the RMS velocity of the molecules is given as 10 to the power 5 centimeter per second, which is like CRMS. And temperature and pressure is known from here, because that is the STP value, standard value. Now the molecular density, that means number of molecules per volume, which is small n, is given also in the question, which is per meter cube. And the diameter sigma of the molecules is 2.5 into 10 to the power minus 10 meter. Then what is the collision frequency between the molecules, which is in part second unit. So basically it is asking, it has given you all the conditions, all the known parameters as the number density of molecules in that gas, then the diameter of each of the molecules, and also the RMS velocity of the molecules in that gas, and the temperature and pressure at that point. And then you have to calculate what is the collision frequency between the molecules. Collision frequency means per unit time, what is the number of collisions that is happening. So it is basically number of collisions per unit time, that is the collision frequency. That is why you have all the options in per second unit. So let us calculate then how to do this. Okay, so first of all, question number 2 is that your number density or number of molecules per unit volume is given as 3 into 10 to the power of 25 per meter cube. That means per meter cube volume contains this many number of molecules. Then the diameter of each of the molecule, this, remember, this is diameter and not radius. So whenever in the question you have given, you are given diameter, then you can directly use this as sigma in the formula and everything. But when it is given as radius, then you have to multiply by 2 and make it diameter, because in mean free path formula everywhere there is diameter sigma that is mentioned and not the radius. So be very, very careful about this. So this is the diameter of each molecule, considering that each molecule is identical in a particular gas. So diameter will be same. That diameter value is given as 2.5 into 10 to the power of minus 10 meter. And the RMS velocity of the molecules in the gas is given as 10 to the power of 5 centimeter per second. So if you convert it into SI unit, that means meter. So 10 to the power 5 into 10 to the power of minus 2 meter per second, which is like 10 cube meter per second, right? And the STP means standard temperature and pressure. That means your temperature is basically 300 Kelvin room temperature, and pressure is basically 1 atmosphere or 1.013 into 10 to the power of 5 Pascal. This is in SI unit of pressure, right? Now we have to get what is the collision frequency. So first of all, let me write down collision frequency you have to get, which is equal to number of collisions per unit time, right? So how to get that? So there is a formula for collision frequency, which is like if the collision frequency equal to velocity divided by lambda, where in this case the velocity will be RMS velocity or sometimes also the average velocity of the gas molecules, whichever condition is given in the question according to that. But basically the RMS velocity divided by lambda is your collision frequency. How? If you just think in your mind that your RMS velocity is basically distance traveled by the molecule per time, right? Distance by time. This is the velocity definition. And then 1 by lambda. 1 by lambda is the basically mean free path, which is the average distance between two collisions. So if you divide the total distance traveled per unit time by the average distance that is there between two successive collisions, then you get what is the number of collisions to travel that distance, right? So the number of collisions to travel that much of a distance by time again. So basically you are getting the collision frequency, or how many number of collisions are happening per unit time. This is your definition. Now if that is the case, then you have F equal to CRMS by lambda, right? And here so you have also this lambda value known from the formula. You can check it out from the lectures, that lambda equal to root over 2 pi sigma squared n. This is a standard formula for lambda that you have to use, where sigma is the molecular diameter, not radius, diameter remember, and n is the molecular number density, which is the number of molecules per unit volume. And because these quantities are given to you in the question itself, so you will just directly use that and you will get that this is equal to root over 2 into pi into sigma is basically 2.5 10 to the power minus 10 whole square. So 2.5 into 10 to the power minus 10 whole squared into n, number density is basically where is number density is this 3 into 10 to the power 25, right? So this is 3 into 10 to the power of 25. So if that is the case, let us calculate then what is this value that is coming. So 1 by root over 2 into pi into 2.5 into 10 to the power of minus 10 whole squared into 3 into 10 to the power of 25. So this value is 1.2 into 10 to the power of minus 7 meter. This is a mean free path value that we have got from the standard formula of mean free path. Now once we have got this, then we just have to directly use the formula of F equal to CRMS by lambda, where CRMS value is also given in the equation, which is 10 cube meter per second. So this is 10 cube in SI unit meter per second divided by lambda is 1.2 into 10 to the power minus 7 meter. So this is meter per second and this is meter. So meter and meter cancels out. So you have just per second, which is the unit of the frequency. So this is 10 cube divided by 1.2 into 10 to the power of minus 7. So this is basically we are getting 8.3 into 10 to the power of 9. So you are getting 8.3 into 10 to the power of 9 second inverse. This is the collision frequency and this is your answer. So let us check with the options. Yes, so this is what we have achieved. So this is option number A and this is correct, right? Now question number 3 is that when a gas expands adiabatically, its volume is doubled while its temperature is decreased by a factor of 1.32. Calculate the number of degrees of freedom for the gas molecules. Okay, so you have a gas that expands adiabatically. So basically it is an adiabatic process, first clue. And you know there is a certain relation between temperature, pressure and volume in an adiabatic, or there are several other like formula, like there is a particular equation for, you know, I think isothermal processes, and then isobaric process when the pressure is constant, or when the volume is constant, isochoric process, everything has a specific formula accordingly. Similarly, adiabatic process means there is no heat that is being exchanged between the system and the environment, but there is no restriction on the temperature, volume or pressure. Neither of those things are being constant. So for adiabatic processes, there is a particular formula or relation connecting the temperature and volume change from one state to another, and that formula is T v to the power of gamma minus 1 is equal to constant, where T is the temperature and V is the volume. Now, why we are using this instead of other equations? Because there are also equations which connects P and V, like v to the power gamma is equal to constant. There is another one with T and P also, which you can get combining these two. But because here there is a physics that is stated in between the volume and the temperature, so that is why we will be using this equation only. So first step is identifying the correct equation to start with. That we have already done. Now there is a certain relation between the temperature of the initial state and final state mentioned, and the volume is also mentioned accordingly. So if you use this formula, you will get a value of gamma from there. What is gamma? Now gamma is just the specific heat ratio, right? So gamma is specific heat ratio, means gamma equal to Cp by Cv. So this is the ratio of the molar specific heat at constant pressure and constant volume of a particular gas. And then you have a direct formula linking the degree of freedom F and the specific heat ratio gamma, which is like gamma equal to 1 plus 2 by F. So once you know gamma, you can directly calculate F from there. So this is the idea that we have to use to solve this question. So let us do that. So question number 3 is that you have adiabatic process in the question. So adiabatic processes are basically what? That your Tv to the power gamma minus 1 equal to constant, right? Where gamma is a specific heat ratio. So going from state 1 to state 2, if the temperature and the pressure are T1 and T2 and the volume temperature are T1 and T2 and volumes are V1 and V2 identified like that. So then according to this equation, you have this product as constant. So even if you are at one state, that means you are at T1 V1 to the power of gamma minus 1, that value will be same as the product value at state 2, which is like T2 V2 to the power of gamma minus 1. Now you have to take the ratio that V2 by V1 to the power of gamma minus 1 equal to T1 by T2. Now in the question it is said that the volume doubled. So undergoing the adiabatic process from initial state to final state, that is state number 2, the volume has doubled. That means V2 is 2 times V1, that, or V2 by V1 equal to 2. So this is 2 to the power of gamma minus 1 is equal to, when also it is mentioned that the temperature has decreased 1.32 by 1.32 factor. That means final temperature is lower than the initial temperature. And what is the connection? That it is factorized by 1.32. That means T1 by T2 is simply 1.32. So here it is 1.32. Now you have to get gamma from here. So just simply take a ln on both sides. So when you take a ln, the power will come in the front. So gamma minus 1, and then rest of the term is just ln 2. And here the right side ln is ln 1.32. So you have gamma minus 1 equal to ln 1.32 divided by ln 2. So you just take the ratio of ln 1.32 by ln of 2, which is like almost 0.4 something. So gamma is equal to just 0.4 plus 1, that is because this minus 1 will come on the right hand side, so this is just 1.4. Now we have to calculate the degrees of freedom, right? So gamma equal to simply 1 plus 2 by f, right? So I think this you know how this relation comes, so I do not have to basically calculate this thing. This is in the lecture most likely. So 1 plus 2 by f is gamma. So if you have gamma is equal to 1.4, then it is 1 plus 2 by f. So then 2 by f is equal to just 1.4 minus 1, which is like 0.4. Then f equal to 2 by 0.4. What it gives you is that 2 by 0.4 is 5. So your f is degrees of freedom is 5. That is your answer. And what can you tell about the type of gas that from this information? If you remember about the degrees of freedom idea, then you know that for diatomic gases the degrees of freedom used to be 5. So diatomic gas means you have two atoms in a single molecule like this. So this is a single molecular construction of that gas, and there is a constant or boundary between them. So m equal to 1, number of constant, and number of atoms here is 2. So your degree of freedom will be 3n minus m, which is 3 into 2 minus 1, that is 5. So here f equal to 5 tells you that the gas given here is diatomic gas. That means like H2, N2, etc., which has two atoms in a single molecule. So this question is done. So here you can check that they have also given the answer as 5. So this is done. Then question number 4 is that if the mean molecular diameter of air be 3 into 10 to the power minus 10 meter, to what pressure must a vessel be evacuated if its mean free path is to exceed 10 centimeter? So the molecular diameter of air, that means sigma, is this. This is diameter, remember. So you are directly identifying it as sigma. Then to what pressure? So pressure is what that you have to calculate. Must a vessel be evacuated if its mean free path lambda is to exceed 10 centimeter. So basically you can roughly say that for lambda is equal to 10 centimeter or 10 into 10 to the power of minus 2 meter, that means 0.1 meter value, and T equal to 273 Kelvin, what will be the pressure in this case? So you have to just know some of the formula and then it will be done. So this is probably question number 4. Yeah. So 4, it asks you that let me write down the quantities. First of all, the molecular diameter of air is 3 into 10 to the power of minus 10 meter. And your lambda, that is the mean free path, is given by 0.1 meter. Then you have to calculate what is the pressure of to which the vessel has to be evacuated. So you know that the formula of this sigma, mean free path, is simply 1 by root over 2 pi sigma squared n, right? So from here you will get what is n, because all other quantities are known to you in the question. Sorry, this is lambda, not sigma. This is the mean free path formula. Okay, so from here you know from the question what is sigma and what is lambda. So if you just put those values, so this is root over 2 pi 3 into 10 to the power of minus 10 whole squared into 0.1. So you will get what is the molecular number density or number of molecules per unit volume. Then if you have that, you know that there is Clapeyron's equation, Clapeyron's equation, I think, that there is a pressure formula as N KT, which we have also used in our earlier week's assignment, because this is a very relevant expression that will come in handy in most of the cases. So P equal to NKT, where K is a Boltzmann constant, that universal constant value you know, and T in the question is mentioned as 273 Kelvin. So T you have to take in Kelvin unit, and N you get from here. So if you put all of those together, you will get first of all K is 1.38 into 10 to the power of minus 23 SI joule per Kelvin into 273 Kelvin divided by N value is this one, or 2 pi 3 into 10 to the power of minus 10 whole squared into 0.1. So if you use your calculator and calculate this, you will get a value of now 0.09 Pascal. But if you look at those options, there is no option given as 0.09 Pascal. So you would think that what there is, like, what part of the calculation has gone wrong. So from here you have to identify. So this is not necessarily always the case, but from here you have to identify, because there are options given. So if you have to get one answer as one of the options, then you have to take this into account, that all the time we do not write the mean free path formula as this with this root 2 factor, because this root 2 factor was not initially there in the rough estimation. This root 2 factor came by the Maxwell's expression of mean free path, right? Maxwell's made some modifications and to actually represent the actual physics, that closer to the actual physics that is going on. So that's why there is an extra root over 2 factor. But in general sense, or in rough approximation sense, so approximate expression of mean free path does not have this root over 2 factor. Then lambda is just root 1 by pi sigma squared n. So you can understand that these are the quantities that remains the same, but root over 2, that is an extra factor that only comes when you take the Maxwell's expression of mean free path. So this is also not wrong, because this is Maxwell expression, but what we have to, why we are doing this in this scenario is that because we have to get an answer that matches with the options given in the question, otherwise it is fine. So you have to use the approximate equation. That means there will be no extra root over 2 factor, which means that there will be no root over 2 factor here. That means basically the answer you have got is divided by an extra root over 2. So to cancel out that, you have to just multiply it as an extra root over 2, and what you get is that just multiply root over 2 into 0.09, which is just I think you have to calculate from the variables, which is coming as almost I think this is not exactly 0.09. I have some estimation made. So basically let us start to calculate from earlier. So what is the value, so what is the value of n in this case? So value of n is 1 by root over 2 into pi into 3 into 10 to the power of minus 10 whole squared into 0.1, right? So this is just 2.5 into 10 to the power 19 if you consider this root 2 factor. But without this root 2 factor, you will have n equal to, which is 3.5 10 to the power of 19 when you take the expression as lambda equal to 1 by pi sigma squared n, and this is the value of n when there is an extra root 2 factor. So to match the answer with the question options, we use this one, the rough estimate. Okay, so then if this is your n, then your p equal to 3.5 into 10 to the power of 19 into 1.38 into 10 to the power of minus 23 into 273. So this is giving you into 1.38 into 10 to the power minus 23 into 273, which is like 0.133. Which is 0.133. This is in Pascal. So this is in SI unit. Okay. So we are getting this as the answer. So you'll see that now the answer matches with one of the options. So this is 0.133 Pascal. This is also answer number C. But just like I said, the root over 2 factor only comes in the Maxwell's expression of mean free path. If you have the liability of matching the answer to the options, then only this you have to do. Otherwise, I think with the root over 2 factor also the answer should come fine. Okay, so let us move on to the next question, that a beam of molecules is passed through a low pressure gas. The mean free path of the molecules is of the gas is 5 into 10 to the power minus 4 meter. Then find the fraction of molecules that do not undergo a collision while traversing the thickness of 5 into 10 to the power minus 5 meter through the gas. So basically they are telling you the value of the mean free path lambda of the gas as this, and then you have to know that fraction of gas, that is n by n naught, which does not undergo a collision while traversing a distance, or the thickness in this case as x. So you know the survival equation, you have to utilize that. So let us move on to the blank page to solve this. Question number 5 is that your mean free path lambda is equal to 5 into 10 to the power of minus 4 meter, and you know your survival equation is n equal to n naught e to the power of minus x by lambda. So the number of molecules that does not undergo any collision within this distance of x is simply e to the power of minus x by lambda. In the question it is mentioned that x is the thickness of the range of 5 into 10 to the power of minus 5 meter. So in this case the fraction will be e to the power of minus 5 into 10 to the power minus 5 divided by lambda is 5 into 10 to the power of minus 4. So this 5 and 5 cancelling out. So e to the power of minus this 10 to the power minus 5 into 10 to the power 4 is 10 to the power minus 1. So this is e to the power of minus 0.1, which is almost 0.9. So this is your answer in this case, 0.9. So let us check whether it matches. So yeah, there is a 0.9, and this is the, so this part has been cropped from here, but this is the correct answer, that is 0.9 in this question. Then question number 6 is that in an assembly of 10,000 molecules, each moving with same velocity, calculate the ratio of the number that would travel undeflected even after traversing a distance equal to 0.5 and 1 times the mean free path. So you have total number of molecules at the starting as 10,000, which is your n naught, right? The total number of molecules at the very first. Then each moving with the same velocity. Okay, so they are having a velocity, they move in unison. Then calculate the ratio of the number that will travel undeflected. So again the survival equation comes into picture, that is n equal to n naught e to the power of minus x by lambda. So the fractional number of molecules that will travel undeflected over a distance of x is e to the power of minus x by lambda. Now that distance can be either 0.5 of lambda, because it is 0.5 times the mean free path, or that distance can be just 1 times the mean free path, which is just lambda. And this fraction you get two different values from there, and then you have to take the ratio of both of them. So basically you have to take a ratio. So you get the two values and take a ratio, and you will get one of these options given in the question. So question number 6, if you try to solve, so I will try to solve here itself. So question number 6 is that your n naught is the initial number of molecules to begin with. So this is 10,000, and using survival equation, the number of molecules surviving after traversing 0.5 times the distance of mean free path is e to the power of minus 0.5 lambda by lambda, which is just e to the power of minus 0.5. And in the second case, when the molecule surviving after traversing a distance which is 1 times the mean free path, which is in this case is e to the power of minus lambda by lambda, that is e to the power of minus 1. So the ratio of both of them will be like this. Fractional ratio is f1 by f2 equal to e to the power of minus 0.5 by e to the power of minus 1. If you take the ratio, you will get 1.65 as your answer, which is your option number A. So let us mark. So yeah, option number A, which is correct from here. Right, so question number 6 is also done. Then you have question number 7, which says that for a hydrogen molecule with a mean free path of 361.5 nanometer, calculate the collision frequency at 300 Kelvin. So first of all, the molecule is a hydrogen molecule, which is like diatomic. That means it is H2, 2 hydrogen atoms in a single molecule. And the mean free path is given in the question as lambda value is this in nanometer. So you have to take in SI, that means in meter. Then calculate the collision frequency at 300 Kelvin. So collision frequency means number of collision per unit time. So you know the idea of collision frequency. The formula is that collision frequency equal to velocity divided by the mean free path, because velocity is the distance by time and mean free path is the average distance between two collisions. So if you divide total distance by this average distance between collisions, you get the number of collisions, and you have already per unit time in the velocity form itself, so that you have number of collisions per unit time. So this is the collision frequency. And so you have directly the idea of lambda, the value of lambda given in the question, but the velocity value is not directly given in the question, that you have to calculate using the other expressions given. So the only other expression that is present here is the 300 Kelvin temperature. So this is the temperature that is given. So you know that the velocities depend on temperature by a specific formula, and in this case we will be using the average velocity of the gas molecules in the hydrogen gas, because there is nothing other than that is mentioned, and we can also use CRMS or RMS velocity somewhere in the question if that is mentioned, but otherwise we will be sticking to the average velocity formula and put it in terms of velocity in the calculation of collision frequency. So question number 7. Question number 7 is that you have hydrogen molecule, diatomic, and your lambda is given as 361.5 nanometer, that means 361.5 into 10 to the power minus 9 meter. And you have to calculate your collision frequency F, which is like C by lambda. Here there is no expression for velocity given in the question, that we have to calculate from temperature, because only the temperature is mentioned. So the temperature is mentioned as I think, what was the temperature, 273 I think, let us check. Sorry, no, it was 300 Kelvin that is mentioned as the temperature. So your T equal to 300 Kelvin. And because we are using the average velocity in this case of definition of velocity in this expression, so your average velocity formula is root over of 8 kT by pi m. That is already covered in week 1 discussion, I think. The average velocity is root over 8 kT by pi m, and this value is 8 into, in SI you will calculate, so 1.3 into the power minus 23 into T is 300 Kelvin by pi into m is mass of a single molecule, mass of each molecule. But because hydrogen is diatomic or H2, so it has 2 atoms, right? So a single molecule has 2 atoms, and you know that for hydrogen the atomic mass is 2 AMU. So 2 is a value and AMU means atomic mass units, which is equivalent to 1 mole of this hydrogen gas will consist of 2 gram of weight or 2 gram of mass. So basically, to get the each mass of each molecule in gram unit from here, you have to just multiply by 1.66 into 10 to the power minus 24 factor, because that was what I had showed in just the last class, that how do you calculate what is the mass value for the molecule. So if you have given in the you have the value given in AMU or atomic mass unit, then to convert into gram unit for a single molecule, the mass is, for a single molecule, it will be 2 into 1.66 into 10 to the power of minus 27. So instead of gram we write in kg. So this is 10 to the power minus 27 kg. So you have pi into 1.66 into 10 to the power of minus 27 into 2. Okay. So this, if you calculate, you will get 1.78 into 10 to the power 3 meter per second. So your collision frequency becomes F equal to 1.78 into 10 to the power of 3 meter per second divided by 361.5, which is the lambda value, 361.5 into 10 to the power of minus 9 meter. So meter and meter cancelling out. So this is just 1.7. So this is just 4.92 into 10 to the power of 9. So this is 4.92 into 10 to the power 9. So this is the answer we have obtained, and the correct answer is also C. So our calculation is right. Then question number 8 is mean free path of nitrogen molecules at STP is given by 6.85 into 10 to the power minus 8 meter. Then calculate collision cross section of the molecules. First of all, for nitrogen molecules, that means diatomic or N2. Mean free path, that is given as lambda. Lambda value is given, and calculate the collision cross section of the molecules, which is basically identified by rho in most of the formulas. So what is the deal here is that question number 8. So what is the meaning of collision cross section? First of all, that we are asked to calculate in the question. So collision cross section is basically if you have a gas molecule which has a diameter of sigma, that means a radius of sigma by 2. So then that molecule, when it can have a collision with other molecules. If you consider that this particular molecule you are dealing with is stable and static. Okay, this is not moving. So any kind of collision that will happen will not be happening due to the movement of this particular molecule, because that we have taken as a standard reference. And then so basically how will then it will go through collisions is basically the other molecules that are present in the surrounding will try to collide with this molecule and give rise to collisions. So what is the effective area within which the collisions are most probable to occur? So this is the dotted area that I have marked here. So this is the effective dotted area of most probable collisions in the system. Why? And this dotted area is not of any dimensions, but it is of dimensions such that it is a circle of radius of sigma. Okay, so the molecule has a radius of sigma by 2 and a diameter of sigma, but the collision cross section area has a dimension of sigma. Okay, why? Because if another molecule which is of the same size as this one, because this one is static, so if the another molecule which is moving comes here, and it will just collide, maximum proximity, it will just collide when they will just touch on each of other surface, and this distance is also sigma by 2, because sigma by 2 is the radius of the molecules. So then if some other molecule comes into that effective cross section area, then we call it that amount of area will be the cross sectional collision cross section of that particular molecule. So this is another gas molecule which is moving, and that comes into the collision cross section area of the first molecule. So basically this effective area is the effective area for collisions to occur to the molecule. So this is your effective collision cross section equal to pi sigma squared, because this is a circle of radius sigma, so the area will be pi sigma squared. So then it will be like pi sigma squared, right? So now you have in the question the value of lambda given, mean free path. So lambda is nothing but root over 2 pi in sigma squared, right? So then sigma squared is obtained as 1 by root over 2 pi in lambda. Okay. Also, so in the question you have this thing mentioned as so basically this is, you know, the Clapeyron's equation of pressure. This is NKT. That means n equal to p by kt. So if you substitute that here, it will be like in the denominator it is p by kt. So this is basically kt by root over 2 pi p lambda. So sigma squared value will be 1.38 into 10 to the power of minus 23 into T is just 273 Kelvin divided by root over 2 into N. N is basically 6.83 into 10 to the power of minus 8 into so the value of P is basically 1 atmosphere, so 1.013 into 10 to the power 5 Pascal, right? So basically let us go back and see what the question was and what are the things that they have provided us. So we have lambda and we have the thing mentioned as STP or standard pressure and temperature, right? So then every value is known to us, so we are just like putting down those known value of the terms in the equation, and we are calculating sigma square, and that is under STP, because STP is the standard temperature and pressure, so P becomes 1 atmosphere, which is like 1.013 into 10 to the power 5 Pascal, and the temperature becomes also 273 Kelvin, right? So sigma squared will be, if you calculate, this is 1.22 into 10 to the power of minus 19. So directly use the idea of cross-sectional area or effective area of cross-section. Pi sigma squared equal to pi into 1.22 to the power of minus 90 whole squared. So this will be 3.83 into 10 to the power of minus 20 whole squared. So 10 to the power minus 19 it will be, and there will be no squared because this is already in sigma square terms. This is just 38.3 into 10 to the power of minus 20. So our correct answer will be, just try to find out which one suits the best. So this is, I think, you have this question correct. So this is the correct answer in this case, B. Okay, so we have two other questions left, and okay, so we have already finished till problem number 8. Then we have two more problems left, and I think we would still have time for some extra one or two problems. So let us do question number 9. It says that the molecular diameter of a gas is 3 into 10 to the power of minus 10 meter. Then calculate the mean free path at temperature 27 degrees centigrade and pressure 1 atmosphere. So sigma, that the molecular diameter is mentioned as this. Then we have to calculate what is lambda, the mean free path, when the temperature is 27 degrees centigrade, which is like 27 plus 273, which is 300 Kelvin, and the pressure is 1 atmosphere, right? So the pressure is 1 atmosphere, means it is 1.013 into 10 to the power of 5 Pascal. Okay, so then so we have to calculate lambda by these parameters when we have these quantities as known. So what do you use for that? So let us go to the page below this. So question number 9 is that sigma is 3 into 10 to the power of minus 10 meter. Lambda equal to, we know the Maxwell's expression of mean free path, lambda equal to root over 2 pi n sigma squared. So, and then you have the information about sigma, but you don't know n, but you know the other things, which is pressure and temperature, right? Because that value is given in the question. So you know the expression that P equal to NKT. So N equal to P by KT. So this is just 1 by root over 2 pi P by KT to sigma squared. This is equal to KT divided by root 2 pi P sigma squared. So you have to now put all the values. K is 1.38 into 10 to the power of minus 23 into T is 27 degrees centigrade, means 300 Kelvin, right? So this is 300 Kelvin. Then divided by root 2 into pi into pressure is just 1.013 into 10 to the power of 5 Pascal. Then sigma squared is 3 into 10 to the power of minus 10 whole squared. So this value, if you calculate, you will get a value of 1.02 into 10 to the power of minus 7 meter. This is your value of mean free path. So let us check and verify which option is correct. So our option number is 1.02. This is option number D. So this is correct. So this is the right answer. Then question number 10 is the last question, is that the mean free path of the molecules of a gas at 25 degrees centigrade. So this means T equal to 25 plus 273, which is like 298 Kelvin, right? And the mean free path of the molecule is lambda. Lambda is this value. So if the radius of the molecule is this quantity, then find the pressure of the gas. Okay. So let us solve this one also. Question number 10. So the radius of the gas is given as 2.56 into 10 to the power of minus 10. Then the molecular diameter is just 2 times R. So you have to multiply it by 2. Otherwise you will use wrong value in the formula, because in the formula sigma is diameter and not radius. So this is this. And then your lambda value is given as 2.63 into 10 to the power of minus 5 meter. So then you know that lambda is equal to 1 by root over 2, same formula, root over 2 pi sigma squared n. So then n equal to just 1 by root over 2 pi sigma squared lambda, which is like 1 by root over 2 pi sigma squared is 2 into 2.56 into 10 to the power of minus 10 whole squared. Okay, and then you multiply it by lambda, which is 2.63 into 10 to the power of minus 5, and this value is almost 134 point something I was getting. So it is almost, you can say, 135 Pascal. So now check the options given, that which is the closest answer. So we have 135 Pascal in the option. So option number C is the correct answer, which is the correct answer in this case. Now since we have still some time left, so I will show you an example, extra example of one or two more problems similar to these concepts. So let us do them. So first problem is that this will be an interesting one because this uses the concept of mean free path, but like the problem is in a different way, but it uses the same concept of mean free path. So it says that, sorry, so first let me write down the question. So the question is, if alpha dt is the probability of a gas molecule having collision in time interval dt, it is the probability of gas molecules making a collision in the time interval dt, then find number A, the probability of a molecule experiencing no collision during the interval t. The probability of a molecule experiencing no collision during time interval of t, and the option number 2, question number 2 is that what is the mean time interval between successive collisions. So you can see the idea is similar, but instead of distance, like the distance was used in mean free path, but here that is used in terms of time. But otherwise the concept is similar to the concept we had used calculating the mean free path idea. So first of all, let us say that the probability of the molecule experiencing no collision in time t, or rather let us call it a free time similar to free path lambda, let us here call it as free time. So the probability of a molecule having no collision in time t will be the same as the probability of a molecule having a free time of t, and that is, let's say, equal to f of t. So answer is that, let's call the probability of a molecule having free time t, or a molecule of undergoing no collision in time t as f of t. So if it is a function of t, then we can also as well say that the probability of a molecule having a free time of t plus dt will be, so probability of a molecule having free time t plus dt is f of t plus dt. So then what is f of t plus dt? Because it is a probability and we know the probability of different events we can multiply, right? So f of t plus dt is the multiplication of two different probabilities. One is the probability of having collision in time t, that is ft, into probability of no collision in the interval dt. sorry, I think I have to rephrase. So there is a confusion in the terminology. So f of t plus dt is basically for the molecule to have no collisions in time t plus dt. So f of t plus dt will be a multiplication of two other probabilities. One is the probability of having no collision in just time t, and the other is the probability of no collision in the interval dt, right? So this will be f of t into, you know that in the question it is mentioned that alpha dt is the probability of a molecule to undergo collision in time dt. That means if you have to calculate what is the probability of molecule having no collision in the dt interval, you just have to subtract it from the total probability, which is 1. So you have basically 1 minus alpha dt. So this is your simple expression of f of t plus dt. Now let us decompose this. So f of t plus dt is now f of t minus alpha f of t dt. So f of t plus dt minus f of t divided by f of t equal to minus alpha dt, right? So this is just f prime t dt by f of t is equal to minus alpha dt. Why f prime t? Because we know the idea of differentiation is that f prime t is f of t plus dt minus f of t divided by dt. So if you take these two on one side, so f prime t dt is equal to just simply this. Okay, then you have to integrate it on both sides. So if you integrate it on both sides, alpha is a constant, so it comes outside integral. So this is ln of f of t equal to minus alpha t plus ln of some constant, which is a in this case. Now you simplify it. So f of t is equal to a e to the power of minus alpha t from here. If you simplify this, where a is the constant. Now we have to get the value of a. For that you have to put a boundary condition. What is that? It is basically that at t equal to 0, that means at initial time when nothing has started, then what is the probability of the molecules having no collision at t equal to 0? So that is f of t equal to 0 equal to f of 0. So this is the probability of the molecule having no collision at time t equal to 0. Now we know that at the initial time there is no collision. So the probability of having no collision will be total 1, because it's the total probability. There is no probability collision of probability. So the total probability of no collision at t equal to 0 will be just 1. So if you put this value in this equation, equal to 1 equal to a e to the power of minus alpha times 0. This e to the power 0 is 1, that means a equal to 1 here. So you can see that f of t is equal to just 1, means a is 1 e to the power of minus alpha t, right? So this is your, I think the first question was that the probability of a molecule experiencing no collision during the interval t. That was our question number A. So this is already nothing but this f of t, which we have already calculated from here in terms of the constants or terms given in the question only. So here we do not have to calculate the value of alpha, because alpha is already there in the equation itself. So it is in terms of that, so it is fine. So question number A is answered. Now question number B says that what is the mean time interval between successive collisions, right? So you have to calculate it the same way you had calculated or derived the expression of mean free path. So mean free time you have to calculate. So it is basically the average free time between successive collisions. Now we'll go by the same approach, that if the probability of having no collision in time interval t is e to the power of minus alpha t, then let's see if initially there are n naught number of initial total count of molecules, which is at t equal to 0 at initial time, right? After an interval t, when there are certain collisions that has happened, so what are the number of molecules that have still survived? N is the number of molecules that survived from the collision or that has not undergone any collision in that interval. Okay, that is no collision for them. That means you can say that your n equal to n naught f of t. N naught is the initial number of molecules and f of t is the probability of the molecule having no collision in time t. So after time interval t, what are the number of molecules that have survived the collision is n. So it is n naught f of t. So n naught e to the power of minus alpha t, where you substitute the value of f of t that you got from question number A. So if this is this, then your dn, if you take a differentiation on both sides, that is n naught is a constant, so no differentiation on n naught, then minus alpha e to the power of minus alpha t dt. This is the derivative you have taken. So your dn, because dn is a number of molecules, so a certain number of molecules, so it cannot be negative, so you have to take a mod sign. So this is just n naught alpha e to the power of minus alpha t dt, right? So this is the basically number of molecules of no collision in the small interval of time dt. Okay, so that means this much number of molecules has a free path length of dt, or this have, sorry, not free path length, I also got confused with the mean free path idea, because the ideas are similar. Here it should be free time. This much have a free time interval of dt. So now you have to calculate the mean free time, that means you have to average it out. So what you do is that mean free time is basically t dn divided by integration of full dn. So we are integrating for all the number of molecules where n can go from 0 to infinity and the time interval is taken as t. So the integration is over n 0 to infinity dn. So this denominator, you know that this is n naught, this is the total number of molecules present initially. So it is 1 by n naught, then t dn 0 to infinity. So you get 1 by n naught 0 to infinity, then dn value you put as n naught alpha e to the power of minus alpha t dt. So this n naught and n naught cancelled out, so you have t alpha 0 to infinity e to the power of minus alpha t dt. So you have t alpha e to the power of minus alpha t by minus alpha from 0 to infinity. So alpha and alpha cancels out, then you have t e to the power of 0 minus e to the power of minus infinity. This is 0 and this is 1. So this is just, what are you left with this? Okay. So we are left with t, but I think, sorry, there is a certain mistake I have made. So I have to basically integrate over time also, that I had missed out here. That is why we are getting again time back in the expression, which it should not be. So just let us correct ourselves. So this is alpha times t to the power of minus alpha t dt, t going from 0 to infinity, right? So the interval, so now the expression comes in terms of the derivative integration is now in terms of t only. Okay, so do the integration by parts. T to the power of minus alpha t dt 0 to infinity minus, first this derivative over t is 1, then again to the power minus alpha t dt, and this total thing is dt integral 0 to infinity. So this is equal to alpha t to minus alpha t by minus alpha 0 to infinity minus alpha t by minus alpha dt from 0 to infinity, which is like alpha, this is minus 1 by, sorry, plus 1 by alpha, let's say, then put 0 first because there is a negative. 0 e to the power 0 minus e to the power minus infinity, already making it in 0. So this is just 0, and this is also 0 times, so this is 0. So the whole thing becomes 0 minus, and this minus plus, then again e to the power of minus alpha t by minus alpha, 0 to infinity. So this is alpha by alpha, then again 1 by alpha e to the power 0 minus e to the power of minus infinity. So you get 1 by alpha, 1 minus 0, which is 1 by alpha. So basically you get your mean free time as 1 by alpha. Now you can see that the concept is exactly similar. The derivations are also exactly similar, only instead of the path length, you have now time interval. Otherwise everything is just equivalent. So another example problem can be like example number 2, let's say. Show that, question is, show that the ratio of speed of sound in an ideal gas to the average speed of its molecule is root over of gamma pi by 8, where gamma is equal to Cp by Cv. So first of all, you know what is the speed of sound of an ideal in an ideal gas. That has a particular formula, so we will use that. Speed of sound in an ideal gas medium equal to Cs equal to root over of gamma P by rho, where gamma is the specific heat ratio, P is the pressure, and rho is the the mass density. So you know from Clapeyron's equation, pressure is NKT, and rho, because it is mass density, mass per volume, so it is m times n, that is mass of a single molecule into the number of molecules per unit volume, which is the molecular number density n, right? So you have this thing, gamma NKT divided by m times n. Then what is the, this is done. Then the other thing that you have to take a ratio of is the average speed of molecules, which is basically a known formula, root over of 8 kT by pi m. Okay, so if you have to take a ratio of these two, Cs by C bar, so if you have basically root over gamma NKT by mn into root over of 8 kT by pi m. So sorry, this will be inverse, so this is inverse because this is C bar is in the denominator. So you have root over gamma NKT by mn into pi m by 8 kT all over root, m and m cancelling out, kt and kt cancelling out. So this is, you have root over of gamma, this n and n also cancels out, gamma pi by 8. So you have the ratio as given in the question determined, right? So these are some problems based on mean free path of gas molecules in an ideal gas and how to calculate mean free path, etc. What are the main equations that we will need for this case? If you just have to write down or list out the main equations that you need to know to solve these kind of numerical problems. So let us write this down at one place. First of all, the main factor is the survival equation, which is n equal to n naught e to the power of minus x by lambda, where lambda is the mean free path, average of all the free path distances or all the molecules in the gas. X is the distance after which n out of n naught number of molecules survive from any kind of collision, or we can say that n number of molecules has a free path length up to x. So if you have to calculate the fraction of molecules surviving after x distance, will be like e to the power of minus x by lambda, right? And this is one thing. fraction, then you have to use this term. Then you have the lambda formula, Maxwell's expression of mean free path, root over 2 pi sigma squared n. Okay, this is Maxwell's expression, where sigma is the diameter of a molecule and n is the number density, that is the number of molecules per unit volume, molecules in the gas. Okay. Sometimes rough expression of lambda is also written as pi sigma squared n. This is not a Maxwell's expression. This is not totally accurate. This root over 2 multiplied factor is more accurate into real case. But this is another rough estimation of mean free path. Okay. If molecular radius is given, then sigma you have to calculate by 2 times r, right? And what else was there is, yes, some associated equations that you needed to substitute in some of the cases is a pressure expression P equal to NKT, where sometimes you have information about N, you have to get P like that. Okay, and rho, the mass density, you know, that is the mass of a single molecule into the number density of molecules, number per unit volume. And what else? I think these are most of the equations that we have covered till now. Okay, and standard temperature and pressure, these values, you know, if this is mentioned and nothing else is mentioned, that means T equal to 300 Kelvin and pressure is equal to 1 atmosphere, which in SI unit if you convert, it will be like 1.013 into 10 to the power 5 Pascal. So these are the things that is necessary. And initially we had also used this expression of gamma equal to 1 plus 2 by f. This is the relation between specific ratio gamma and f is the degree of freedom. Okay. Also, important thing, collision frequency is the number of collision per unit time. That you have to calculate. Then you have to give the velocity of the molecules divided by the mean free path. Okay. Or sometimes if RMS velocity is not there, then you also use the average velocity of the gas molecules by mean free path. That you have to choose accordingly. If the question has mentioned the value of mean free RMS velocity, then use this. Or else if they have just mentioned the temperature, then you can use the average velocity formula, which is C bar equal to root over of 8 kT by pi m. So these are the some of the main equations that we will need, and it will suffice for solving any kind of numerical solution problems which are in terms of these mean free path or these concepts. Okay, so I think this week's assignment is done. Then we'll meet in the next week.